Okay, can you see my monitor? Today we will continue the previous lecture material, which is the rotational motion, and we will start now with the rolling motion. Yesterday, I will remark and remind you that we study yesterday the rotational motion in the place of the linear motion. And simply, our formulas will be in theta, omega, and alpha in the place of x and v and the acceleration a. Now, okay. Now we will continue. We have something called the rolling motion, which is the part that we can connect between the linear and the rotational motion. We need to put this example. If we have a car, and this car is moving by a velocity v car, it is to the positive x-axis, as you see here. We don't care about the direction now. We are dealing with the theta and the radius and so on. Now, as you see, if the car going forward by a velocity v car, its wheels are moving by a rotational motion, and the radius for each wheel is r, as you see here. And there is a tangential velocity for this wheel, which is the same at all the parts of the wheel. In the bottom of that wheel, that velocity, the tangential velocity, is backward, as you know. Because of that, the car will move forward. Starting from this point on the wheel, which has a radius r, our car moved a displacement which is delta x equal to 500 meters during a time delta t is 50 seconds. Can we find the velocity now? The answer is yes, we can find the velocity. It is delta x over delta t, as we know from before, which is 500 over 50, which is 10 meters per second. This is the velocity of the car. If the radius of each tire is 30 centimeters or 0.30 meters, okay, what if we need to find the omega, or the angular velocity of the tire? The angular velocity is, from the previous lecture, we see that omega, or v tangential, is equal to r multiplied by omega. And v tangential, in our case, it is equal to the velocity of the car, but in the opposite direction, right? Now look, the direction of the rotation, it is clockwise. And I said yesterday that the motion clockwise means negative sign. The motion counterclockwise means positive sign. So v tangential is negative velocity of the car, which is negative 10. Now what about omega? Omega is v tangential over the radius. So the magnitude of this omega is 10 over the radius, which is 0.3. It will be 33.3 radian per second. And its direction is negative, just as you see here from the velocity of the car. So this has a negative directions, or we need to put clockwise, not counterclockwise. Okay. Now, if I need to find number of rotations for the tire to pass 500 meters, how many rotations this tire will rotate to complete this distance? We have, it is not drawn here, this distance of the tire will repeat itself many times. We need to know the number of these times. What is this distance? It is the circumference of the tire because it is a circle. It is 2 pi r for a circle. So it is 2 pi r. And we have the total distance, which is 500 meters. If we divide this over this period or over this distance, which is 2 pi r, it will give us the total number of rotations. So delta x, which is 500, divided over 2 pi r, which is 2 pi 0.3 multiplied by it, it is equal to 265.26 rotations. So the tire, it will rotate 265 times to complete this distance. Okay. In this case, we connect between a linear distance and a rotational distance or circumference of a rotating circle. Okay, what else we need to find? What is the time? Okay, now we know omega. We know the velocity, which is V tangential for the tire. What is the time to make a total rotation? The time to make the total rotation, it is the distance or the distance divided over the velocity. The velocity is Vt for just for one rotation. It is Vt 2 pi r over Vt. If you calculate it, it will be 2 pi. If you multiply it by r and multiply by r here, you have 2 pi r. It is the circumference. If you have another r here, omega r, it is v. So it is a distance over a velocity. This will be equal to the time for each rotation, 2 pi r of 2 pi over omega. Now, the total time is 50 seconds. We have 265.26 rotations. So we have 265 rotations during 50 seconds. If we divide the 50 seconds over the number of rotations, it will give us also the time for each rotation, which is the period, which is almost 0.2 seconds. Any question about this? Okay, now at this point, we finished the equations of motion for the rotational motion. Now we'll move for maybe Newton's law and rotational motion, maybe the kinetic energy laws in rotational motion. Here we will deal now with the kinetic energy before talking about Newton's second law. I think we can start by it by studying or discussing Newton's second law of rotational motion today. Okay. Now, if we need to study the kinetic energy in the rotational motion, we know that from before, the kinetic energy in linear motion is equal to half mv squared. But remember that V is equal to R omega. V is equal to R omega, but it is squared. So it is R squared omega squared. Now we have in the place of mv squared, we have r squared omega squared, and the half is the half. We can reorder our quantity like this. The kinetic energy will be equal to 1/2. Before we have a velocity, now we have angular velocity, so we need to keep the velocity as a separated quantity. So we have angular velocity, not the velocity. Okay, we have r squared. What we need to do with it? We can combine it with the mass. We don't have a mass. Now we have another thing. We have r squared. It is another mass, or it is another effect of the mass. It is the rotated mass with the radius r. Assume that this is the center of rotation, and this is r, the radius of rotation, and this is the mass. And this mass is rotating about the center by angular velocity omega. This is omega. This is the mass, which is m. This is r, which is r squared here. If we increase r, then the effect of this rotation will change. If we change the mass, the effect of this kinetic energy will change. Also the omega, if we change it. Now we have a new thing. We have a new quantity. It is the mass, but in the rotational motion. Okay? So this mass has a rotational effect. Okay? This quantity, or the rotational effect of this mass, will be named as a moment of inertia. We know that if this mass is here and we need to rotate it, it is different. It needs different amount of force if we change the position of this mass. If we put it at the middle of the radius, it needs a different amount of energy or force to rotate it. But the mass m is the same, but the radius will change. Because of that, in the rotational motion, we don't have a mass. We have a moment of inertia. Okay? Which represent the rotational effect of the mass. We need to name it. In physics, everything has a name, has a symbol, has a unit. So the moment of inertia, we can name it as I, which is mr squared. For a point mass, this is a point mass away from the center by the radius r. Okay? What if we have more than one mass? Remember the center of mass, we have m1 plus m2 plus m3 and so on. We can add the total many masses together. Here also we can add many moments of inertia together. If we have more than one rotating object, then we can add the moment of inertia for all of them. So the total moment of inertia for many masses, it is m1 r1 squared plus m2 r2 squared and so on. Any question about this? Now we have the kinetic energy, which is half mv squared. It is equal to a new thing, which is 1/2. mr squared will be I now. We will see it is I, which is the mass in the rotational motion. Here, this is the velocity in the rotational motion. It is the same picture, but it is in the rotational motion. So this is the kinetic energy. It is 1/2 I omega squared. This is the rotational kinetic energy. Okay? It is in the same picture. It was 1/2 mv squared. M is the mass in linear motion, like you see here, which is the normal mass. And the velocity, it is the linear velocity. Now we will deal with the rotational motion kinetic energy. Now, for a point mass, we can assume the mass just as m, like here. And the radius is the radius from that point to the center of rotation. It will be just one radius because it is a point to point. So we have just one radius. But what if we have many points? As you see here, we have this is the first radius. This is the second radius for a second point mass. This is a third radius for a third point mass, and we can add them together. The moment of inertia for all of this system. But what if we have, for example, I will show you these objects. If we have this object, which is a disk rotating around an axis passing from its edge. Where is the radius? The mass is the total mass of this disk, but where is the radius? Is it from the axis of rotation here, center of rotation, to the center of the radius of the mass, or for any? We have many radii here because this object is not a point mass, it is extended object. Because of that, we cannot consider the moment of inertia for an extended object as the point mass. There is a way to compute the moment of inertia for these objects, and we will not do this derivation, but it is given just in the book. It is in, I don't know what is the page, but this is table 10.1. For example, for a hoop rotating around an axis passing through its center, the moment of inertia is mr squared. It is the same as the point mass. For a disk, which is a solid hoop or closed hoop, it is 1/2 mr squared. You can see mr squared is always exists, but we have a different factor for each shape. This is the same disk, but rotating about an axis passing from its edge. It is 3/2 mr squared, not just 1/2. Look for a rod, okay? It is rotating about its center of mass or its midpoint like this. It is 1/12. But if the axis of rotation at its end, it will be 1/3 ml squared. Ml squared, almost mr squared. It's okay. And the same for different objects. This is a hollow sphere. This is the solid sphere rotating about its center. This is a solid sphere rotating about an axis at its edge. This is a solid plate, different shapes of rotations. And we have mr squared, mr squared, mr squared, and so on. But the factor is different from shape to shape or from rotation to rotation. Now, this will be given to you in the exam or in any example to be solved. You don't need to cover this in your mind, okay? You know from before the kinetic energy is 1/2 mv squared. Now it will be 1/2 I omega squared. Omega is the velocity, it will be given. It is simple to be found. It is mr squared, but there is a factor, depends on the shape or the object, rotating object, okay? Okay, I think there's an example. Yes, we have it. Okay, look at this example. This example, it contains old example and the new example. We need to see the difference between them. Look at the old one. We have a system, a hill, a mass. This mass initially at point number 1, then at point number 2, then at point number 3. We solved this example from before. And we need to find the total mechanical energy at each point. So at point here, its velocity at this point 1 is 0. Its height here is h is 3 meters. The mass is 5 kilograms. This mass, as you see, it is a block or a box, and this box is sliding without any friction force. We have the same system here, but with a ball, and this ball will not slide, it just rotating. The same mass, 5 kilograms, the same altitude, initial altitude, and we need to know its radius, because we need to find many things using this radius. For example, we need to find the moment of inertia for that solid sphere, which is 25 mr squared. We will use it here. We need to compare between the motion as we learned from before without rolling or without rotation and with rotation. Is there any difference between the energies or the mechanical energies or what? Okay, sorry. Now, let us solve the first example. We have the mechanical energy at the first point should be equal to this mechanical energy should be equal to the mechanical energy at this point. The mechanical energy, as we know, it is equal to the kinetic energy plus the potential energy, which is potential due gravity. We don't have any spring. We don't have any work done by the friction force. So it will be 1/2 mv squared plus mg h or y at point number 1. The velocity here is 0, as you know. The potential energy mg h, which is 3, it will be always, we see this number 147 joules. It will be equal to the mechanical energy at point number 2 and at point number 3. At point number 2, the mechanical energy, because we have this is the 0th level, the potential energy now at point number 2 and at point number 3 is equal to 0, the potential energy, because the height is 0. You will see that the kinetic energy plus the potential energy at point number 2, which is 1/2 multiplied by the mass, because the kinetic energy 1/2 mv squared. V squared, we don't know the velocity, plus the potential energy, which is 0. Now the potential energy is equal to 0. So all the kinetic energy is equal to the all mechanical energy, which is 147. We can find the velocity. Now 147 is equal to 5/2 multiplied by velocity. 5 is the mass now. So the velocity is the square root of 2 multiplied by 147/5, it will be 7.7 meters per second. It will be the same also at point number 3. So the velocity here is 7.7 meters per second. I'm talking about linear velocity. Okay. Now here we have rotational velocity. We have rotational kinetic energy too. Now here in the first example, we just have a linear motion. But in this example, we have linear motion. As you see, we have V, which is a linear. We have omega, which is a rotational. So we have two kinds of motions. So the mechanical energy will be equal to the kinetic energy, which is the linear, plus the kinetic energy, which is the rotational, plus the potential energy. At point number 1, we don't have any velocity. The velocity is 0, and the rotational velocity or the angular velocity is 0 too. So as you see here, the first term is 1/2 mv squared plus 1/2 I omega 1 squared. Now here we have I omega for the rotational motion, not mv, plus mg h squared. So the velocity is 0, the rotational velocity or angular velocity is 0 too. And the mechanical energy will be equal to the potential energy, which is the same like this one, which is 147 joules, which is equal to the mechanical energy here and the mechanical energy here. This concept is called, as we see from before, the conservation of energy. Okay. Now we need to find I. We don't know what is I. We know the mass. We know the radius. It is not r squared because it is not a point mass. For a solid object, it is 2/5 solid sphere. It is 2/5 mr squared. I use it here to find I. 2/5. The mass is 5. The radius is 0.3 squared. It will be equal to 0.28 kilogram meter square. Because we know that the mass is measured by kilogram. It is multiplied by r squared. The r squared is meter squared. So the moment of inertia is kilogram meter squared. Kilogram meter squared. So we know I now. We know m. Okay, what we need to continue solving. At point number 2, the mechanical energy, again, it is constant, 147. It will be equal to the kinetic energy at point number 2 plus the kinetic rotational energy at point number 2 plus the potential energy at point number 2. The potential energy at the 0th level is 0. You will see that. So 147 equal to 1 mv squared at point number 2 plus 1/2, 2/5 mr squared, which is I, we just found it, multiplied by omega plus mgy. This term is 0 because we are at the 0th level. Look, it is 0y. Okay. Now we have we have 147 is equal to 1/2. The mass is 5. V2 squared. We don't know it. Okay, what else? We have 1/2 I, which is 0.18 as we found it, multiplied by omega 2 squared. We don't know omega 2. Plus 0. Now we have two unknowns quantities, which are the velocity and the angular velocity. How can we find them? We find them. So we have two quantities to be calculated. Now we know a relation between V and the angular velocity omega. There is a relation. We know that V is equal to R multiplied by omega. We know that from before. And in other words, omega is equal to V over R. But we have omega squared, we have V squared. So omega squared is equal to V squared over R squared. There is a relation between them. So we can use this relation to replace one of them. We can solve it for just velocity. Keep the velocity. Use omega squared as V squared over R squared. R squared is given 0.3 V squared. Now we have all the equation with just unknown quantity, which is V2 squared. We can find now V2 squared. Let us continue. By organizing, take V2 as a factor from these two terms, you will find that 147 is equal to this factor multiplied by V2 squared, which is 3.5 V2 squared. Okay, divide over 3.5, 147 over 3.5. Under the square root, because we have V2 squared, you can see here I didn't put plus minus because I assume the motion in one dimension and it is the positive x direction. It's okay to have the positive, it is the speed in the positive direction. So the velocity now, it is 6.5 meters per second. It is different than the block velocity, which is 7.7. Why that happened? we have a different velocity, we have the same mass, the same experiment, but a different shape. Because we have a rotational motion, we have a different final velocity difference between the two objects. Now we have a part of the energy for the ball go for the rotational motion, but all the energy for the block goes for the linear motion. Here, the kinetic energy or the mechanical energy spent for the rotational kinetic energy plus the linear kinetic energy. So we have something else consume this velocity. Where's the difference from 7.7 to 6.5? We can see that. We can find omega now from this relation. Don't worry about this. The kinetic energy will still the same. Now, if I ask you to find the kinetic energy, the total kinetic energy for this ball, it will be equal to the kinetic energy for the linear motion plus the kinetic energy for the rotational motion. The kinetic energy for the linear motion, it is 1/2 mv squared. This is v, what we found, which is 6.5 squared. Plus the rotational kinetic energy, which is 1/2 I. We found I here, 0.18, multiplied by omega squared. Omega squared is v squared over r squared. Okay, v squared, this is v. R is 0.3 squared. This is omega, by the way. Omega is 6.5 over 0.3. It will be almost maybe 22 or something like that. Now, the total kinetic energy is the total mechanical energy, which is 147, as we know. Now, if we compute this, it will be almost the real linear kinetic energy. It is 105 joules. The rest of the mechanical energy is a kinetic energy for the rotational motion, which is 42 joules. Now, if you go back to the box and you compute the kinetic energy of this velocity, it will be 147. We found it from it. The total mechanical energy comes from this velocity. Now, the total mechanical energy for the ball comes from the linear velocity plus the rotational velocity. So we have rotational kinetic energy equal to 42 joules. Altogether will be conserved to be 147 joules. Any question about this now? This is the last part in chapter 11. Okay, we talk about again, we talked about the comparing between the linear and the angular motion. We moved our study from the linear motion to the angular motion, and we know the relations between the linear quantities and the angular quantities. We see there's accelerations also in radial direction and tangential direction, but we didn't deal with the Newton's second law yet. And now we just solve an example on the rolling motion, which is a connection between the linear and the rotational motion, then the kinetic energy. As you see, the potential energy will not change because it is just a position for that mass. And there's a new quantity, which is the moment of inertia, which is a property of a rotating object. And this property depends on the mass and the radius of rotation and the shape of that rotating object. And this is an example we compared between the traditional moving object or block versus the rotating ball or solid ball. And we see that we have two kinds of kinetic energy. Okay, now this is all about this chapter. I can move to the torque now. Any question about this chapter? I will talk about chapter 12, not 10, it is 12.1, which is the dynamic of rotational motion. And I will talk about the torque. This sample is tau, which is the sample torque. Now, we need to deal with another level in the rotational motion in our study, which is the Newton's second law. We need to deal with the forces. From before, we know that if we affect by a force on any object, we can move this object to the left, to the right, to the top, and by a force, this force will move the object to all of the object, and it will not rotate that object. If we need to move this tool from here to here, just we need to apply a force, then it will be moved from here to here by this force. But now we have a rotational effect. The rotational effect means we have a rotation about a center, as we see from before. Here we don't have any rotation. Even if you see I put some centers to rotate about, but we don't have these rotations. Here we need to start thinking about this rotational motion. If this is our center of rotation at this screw, and this is the screwdriver or the key to rotate this screw, if we apply a force, we can apply this force at any point on this tool. And this point has a distance from the center of rotation, which is R, as you see, from here to here. And this force has an angle from this radius. This is the angle. Because the radius from the center to the point where the force is acting, this is R from here to here. So the direction of R is outward from that point. So this is R, the direction of R. And this is our force. We need the angle from R to the force. So it is counterclockwise from R to F. This angle may differ from experiment to another experiment. Sometimes the force is in this direction. Sometimes it is in this direction, and so on. So the force has a name, which is a force. We deal with it by using Newton's second law. But now we don't have just a force. If you remember, I will go back to show you this thing. We have a mass, but no, not this one. This one. We have a mass in general, okay? But now we don't have a mass. We have moment of inertia. We have the rotational effect of the mass. By the same way, we have a rotational effect of the force. Here we have a rotational effect of the force. Depends on the force, which is a vector, depends also on the radius, magnitude, and direction, which is another vector, and depends on the relative direction between them, which is the angle between them, okay? So this is the torque, which is the rotational effect of the force. It is the torque, okay? Any question about the torque? It is just the force, which is the linear force, but in rotational motion. So how we can define the torque? Tau. It is just R cross product or vector product with the force F. There are two vectors. We will not deal with the cross product or the vector product like you see here. We will just use the magnitude of the torque. This is the absolute value for any vector is equal to the magnitude of that vector. For the torque, it is R F sine theta. R cross section, cross product with F, it is R F sine theta. The work from before, if you remember it, it was R dot F. It was R F cosine theta, but now we have the sine theta. If we use the sine, then we mean a different distance. It means the perpendicular distance from the center of rotation. So we need the effect of the perpendicular F to the radius. So this F has two components. One of them is in the direction of the axis R. The other component is perpendicular to that direction, which is R. We need the perpendicular effect. We don't need to use the parallel part. The parallel part, we use it in the linear motion when we computed the work. Okay, let us look here. What is the units of the torque? The radius, it is measured in meters. The force is measured by newtons. So the units of the torque is Newton meter. But it is not a work. The work was Newton meter or joule. Here it is not an energy. It is not a work. It is just a torque. Okay, its unit is just Newton meter. We cannot convert it to joules. As we know from before also, if we have many forces, we can add them together. So if we have many torques, we can add them together. So the total torque is equal to torque 1 plus torque 2 plus torque 3 and so on. Okay. So it will be R1 F1 sine theta 1, R2 F2 sine theta 2 and so on. We can see that doing some examples. Any question about the torque? Okay. Now, what if we have this rod, this stick, and this is the center of rotation or axis of rotation at point number 0? We don't have XY plane here. We just have a rotation. We have 3 forces, and you can see the direction of each force. For example, the first force acts at the point number 1 here. The radius is to this direction, going away from the center of rotation. We need to find the angle from the radius to the force. So it is counterclockwise, as we said from before. So this is theta 1. You cannot tell me this is theta 1. It is from R to F. This is for the first force. We can find the first torque for it by knowing the radius, by knowing the theta, by knowing the force. The second force at the second point, it is a different radius, it is a different angle, it is a different force, which is F2. Also here we have F3 with a right angle, which is 90 degrees. So the forces are 5, 10, and 10. 1, 2, 3. And thetas, which are the angles, the first angle, which is 200 degrees. The second angle is 100 degree. This is 100 degree. The third angle is 90 degrees. Here. The radius of the first force is 1.2 meters. The second one is 2 meters. The third one is 3 meters. Just the numerical values. And we have this relation. We need to find the total torque. That's it. Okay, let us do it. So the torque from the first force is the radius, which is 1.2 as given here. The force is 5. it is 5. Then sine theta. Theta counterclockwise from R to the force, it is 200. So the torque is negative 2.05 Newton meter. The negative sign comes from the sine 200. Sine 200 is negative. And we will discuss that now. What about the second torque for this force, which is this one? It is R2 F2 sine theta 2. It is 2 meters multiplied by 10 newtons multiplied by sine theta, which is sine 100. It is 19.7 Newton meter. Newton meter here, it is a unit of the torque. It is not a work. Okay, it is not joule. As I put this note here. The third torque is R3 F3 sine theta 3, which is sine 90, which is 1. So it is 30 Newton meter. The total torque, we need to add them together just as forces. Add them together, then the total torque will be 47.6 Newton meter. It is simple, just apply the relations. Now, for each force, for each torque, we have a direction. You will see that now. For the force number 2, its effect is counterclockwise. We deal from before that any counterclockwise is positive. So we have a positive torque for F2 and F3. Yes, you're right. For F2 and F3, we have positive torques, but negative torque for F1 because its rotational effect is clockwise. So the direction of the torque has a sign. So the positive torque is counterclockwise. The negative torque is clockwise. Is that clear? So if you rotate your hand counterclockwise, then it is positive rotation or positive torque. Clockwise is negative. It is just Newton's second law. Okay, when we see when the work is equal to 0, now we can see sometimes the torque is equal to 0. If the radius is 0, the torque is equal to R F sine theta. So it depends on 3 quantities, R, F, and theta. If R is 0, then the torque is 0. If we affect on, for example, if we need the door in the classroom or in your room is rotating about its axis. If you act on the door at the point of rotation, which is the edge of the door at the axis of rotation, and you need to open that door, you will not be able to rotate it because R is 0 at this point. So if we affect by any force at this point at the axis of rotation, this effect will lead to 0 torque. What about force is equal to 0? Yes, if we have no force on that rotating door, then the torque is equal to 0. For example, if there is a fly come to push the door, its force is almost 0, then its torque is equal to 0 because it doesn't have any force. What about sine theta? We know that sine theta is equal to 0 when theta equal to 0 or 180 or 360 and so on. If you try to pull the door to this direction or push on it to the opposite direction of the R of the radius, because this is a radius, if your angle here, the angle is 0. If you apply by 1,000 Newton, but theta is equal to 0 here because the radius in the same direction. The radius, the theta between the radius and the force is 0 now. Now, and the radius, whatever the radius is, then the torque is equal to 0. If you pull the door to this direction, it will not affect on it rotationally. If you push it on to this direction, also there is no rotational effect. okay? So we have zero torque for these conditions. Maybe I will ask you in the final exam, what is the conditions to just like I did for the work in the second midterm exam. Okay, this is the last thing. We have the torque has a direction. If we have a force, this force has an angle between the force and the radius r. This is a rotating object. It will rotate the object rotate by a velocity, which is a tangential velocity. The rotational axis, just as we said from yesterday about the rotation about an axis, then the rotation direction is along that axis. So if we have this is R, this is F, the direction of the torque is perpendicular to these two vectors. Okay. So we have a direction of the torque. I can show you this image. The torque animation, you can see here. If we will not deal now with the L, we are dealing with tau equal to R cross F. F is the blue arrow. This is F. It is horizontal, as you see. R is the radius, which is the red one. Tau, which is the move or the violet arrow. When the rotation, look, when the rotation is counterclockwise, the torque is positive. When the rotation is counterclockwise, the torque is negative, as we see that from before. Look, I need to stop it. I can't stop it. But now look, the force clockwise, the torque down or negative. Okay. This is all about today's lecture. We finish chapter 11 and we start chapter 12. And we'll continue chapter 12 tomorrow and the next day. And I will discuss the exams, questions, maybe tomorrow. I will solve them, or I will show you how to solve. And that's it. Any question for today? I'll stop recording at this point. Thank you.